On October 19th, 2017, a telescope named Pan-STARRS S1, sitting on top of a volcano in Hawaii, caught a single point of light moving across the sky in a way that no comet, no asteroid, and no piece of space junk had ever moved before. It was traveling at 196,000 miles per hour, and it was not orbiting the sun. It was passing through. Within days, astronomers around the world had confirmed something that had never been confirmed before in the history of astronomy. This object did not come from our solar system. It came from interstellar space, from somewhere else entirely, and it was leaving just as fast as it had arrived. They named it Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. And for a few short weeks in the winter of 2017, before it faded beyond the reach of even the most powerful telescopes on Earth, Oumuamua became the single strangest object anyone had ever tracked moving through our solar system. That is not an exaggeration, and it is not clickbait. It is the plain, documented, peer-reviewed truth. This object broke pattern after pattern that scientists thought they understood about comets and asteroids, and it did so in full view of some of the best instruments humanity has ever built. It came, it startled an entire scientific community, and then it left. The question that has haunted researchers ever since is not really whether Oumuamua turned around and came back. It did not, and we will get into exactly why that persistent rumor exists and why it is false. The real question, the one that actually matters, is what Oumuamua was, why it behaved the way it did, and why, years later, we now know for a fact that it was never a one-time fluke. It was the first confirmed member of a family, and that family has already grown twice more since 2017, with 2 additional interstellar visitors now cataloged, tracked, and in one case, still being actively studied by observatories around the planet as you listen to this. Let's start with the shape, because the shape is where this story stopped feeling ordinary. When astronomers first spotted Oumuamua, they assumed it was a comet, the way you'd assume any fast-moving icy body passing near the sun would be. But comets have a signature, a glowing coma, a tail of gas and dust streaming away from the nucleus as sunlight vaporizes its ices. Oumuamua had none of that. No tail, no coma, no visible outgassing. It looked, through every telescope pointed at it, like a bare, solid, naked rock, or metal, traveling through the void. That alone earned it a reclassification from comet to asteroid within days of discovery. But then the brightness data came in, and things got stranger. As Oumuamua tumbled through space, its brightness varied by a factor of 10 over the course of its roughly 7.25-hour rotation period. Astronomers led by Karen Meech at the University of Hawaii's Institute for Astronomy pored over that light curve and arrived at a conclusion that, on paper, sounds almost impossible. Oumuamua had to be extremely elongated, at least 5 to 10 times longer than it was wide, possibly resembling a cigar or a flattened, elongated slab. No known asteroid or comet in our own solar system, out of the hundreds of thousands cataloged, comes anywhere close to that ratio. The most extreme shapes we'd previously observed among solar system bodies were maybe 3 times longer than they were wide. Oumuamua blew past that by a wide margin. Later refinements to the data suggested it might be more pancake-shaped than cigar-shaped, flattened rather than cylindrical. But either way, the underlying fact held. This was a shape unlike anything astronomers had catalogued before, spinning end over end, tumbling chaotically rather than rotating smoothly, which told researchers it had likely been tumbling like that for a very long time, possibly since some ancient collision flung it out of its home system in the first place. Before we even get to the shape, it's worth sitting with just how narrow the window of discovery actually was. Oumuamua wasn't found on approach, the way 3I Atlas would be years later. It was found already outbound, already past its closest point to the sun, already fading. From the moment Pan-STARRS S1 flagged it on October 19, 2017, astronomers had roughly 11 weeks, a little over 2.5 months, before the object dimmed beyond the reach of even the largest ground-based telescopes on Earth. Compare that to the years of lead time researchers eventually got with 3I Atlas, and you start to understand why Oumuamua remains such a stubborn scientific puzzle. Every single measurement, every spectrum, every brightness curve, every estimate of its size, shape, and composition had to be captured in that brief sliver of time, using instruments that, in late 2017, simply weren't designed with an object like this in mind. Scientists were essentially trying to build a complete profile of a completely unprecedented visitor while it was already halfway out the door. That's part of why so many questions about Oumuamua remain open even now, years later. Not because scientists didn't try hard enough, but because the object gave humanity a genuinely tiny window to work with. And then it was simply gone. Too faint, too far, and too fast for any telescope we had. Then came color and composition. Oumuamua had a reddish hue, consistent with an object whose surface had been baked by billions of years of cosmic ray exposure during its long journey through interstellar space. A kind of weathering that only happens to something that has been drifting alone, far from any star, for an immense length of time. Spectral analysis suggested a surface that was dense, rocky, possibly containing metals, and critically, showing no evidence of water ice on the surface. This fit the picture of a solid, compact body. NASA's own account of the object describes it as dense and rocky, its reddened surface consistent with prolonged irradiation, with no signs of water or ice detected. On the surface, then, Oumuamua looked like exactly what a reclassification to asteroid would suggest. An inert hunk of rock tumbling through the solar system on a one-way trip, minding its own business. And then it did something an inert hunk of rock should not do. It accelerated. As Oumuamua sailed away from the sun, astronomers tracking its exact position noticed something that did not add up. Based purely on the sun's gravity and the trajectories of every other object we've ever tracked, Oumuamua's path should have been fully predictable. A clean, hyperbolic curve dictated entirely by gravitational physics. Instead, the object was picking up extra, unexplained velocity as it departed. A small but measurable non-gravitational acceleration, the kind of subtle push you'd expect from a comet venting gas from its surface like a tiny, lopsided rocket thruster. That's exactly the mechanism astronomers have relied on for decades to explain why comets in our own solar system sometimes deviate slightly from pure gravitational paths. As ice sublimates unevenly off a rotating, irregular nucleus, it produces thrust, nudging the object's course. The trouble was, Oumuamua showed absolutely no visual evidence of outgassing. No tail, no coma, no dust cloud, no detectable gas. Every instrument that looked for the telltale signs of a vaporizing comet came up empty. Yet the acceleration was there in the data, real and measurable, and it needed an explanation. This is the exact moment Oumuamua stopped being just an interesting oddity and became one of the most debated objects in modern astronomy. Because when your data doesn't fit any of the models you already have, scientists start generating new ones, and in Oumuamua's case, they generated quite a few. The leading, most broadly accepted natural explanation is that Oumuamua was, in fact, releasing gas, just not in a way our telescopes were built to detect. One influential 2021 study proposed that Oumuamua could have been made largely of frozen molecular hydrogen ice, a substance that would sublimate, turn directly from solid to gas, quietly and invisibly under sunlight, without producing the bright, easily photographed dust tail typical of water ice comets. If a chunk of that hydrogen ice had been chipped off a larger parent body in some distant star system, buried molecular hydrogen inside it could slowly boil away as it warmed near our sun, providing exactly the kind of subtle propulsion astronomers measured, while leaving almost no visible trace. It's an elegant idea because it explains the acceleration without requiring anything exotic, but it also requires molecular hydrogen ice to form and survive interstellar travel in a way that remains debated among specialists, since that ice sublimates at extremely low temperatures and might not survive the journey intact. A separate and increasingly favored explanation, published by researchers examining Oumuamua's behavior in the years since, points to hydrogen gas produced through cosmic ray processing of water ice, or to other volatile ices, like carbon monoxide or carbon dioxide, embedded within a mixed icy rocky body, essentially proposing that Oumuamua behaved at its core like a comet after all, just one whose outgassing signature was too faint and too diffuse to photograph with 2017-era telescopes at the distance it was already receding to. Some scientists have grouped Oumuamua into a broader, newly recognized category some now call dark comets, small solar system bodies that show measurable non-gravitational acceleration, but no visible cometary activity, a category that researchers have since identified among several objects that never leave our own solar system. If Oumuamua was simply an early, extreme example of a dark comet, it suggests these things might not be rare freaks of nature at all, but a whole quietly overlooked class of object we're only now learning to recognize. It's worth pausing here to appreciate why the dark comet idea matters so much beyond just Oumuamua itself. If researchers are right that this represents a genuine, previously unrecognized class of object, it means our solar system, and by extension other star systems, may be quietly full of bodies that look inert through a telescope, but are actually being gently nudged by faint, undetectable outgassing the entire time. Several objects orbiting entirely within our own solar system have since been flagged as candidate dark comets, small asteroids whose measured trajectories don't quite match pure gravitational predictions, with no visible tail or coma to explain the discrepancy. If that's the case, Oumuamua wasn't some singular anomaly defying the laws of physics. It may have simply been the first, most extreme, most attention-grabbing example of a category of object that had been hiding in plain sight all along, one that we only started actively searching for because Oumuamua forced astronomers to ask the question in the first place. And then there's the explanation that captured global headlines and refuses to fully die down: the possibility that Oumuamua was artificial. This idea is most closely associated with Avi Loeb, the Harvard astrophysicist, who, along with a colleague, published a paper in 2018 arguing that a light sail, an extremely thin, artificially manufactured sheet of material designed to be pushed by sunlight, similar in principle to a solar sail humans have actually built and tested for our own spacecraft, could explain Oumuamua's extreme elongated shape, its lack of visible outgassing, and its subtle non-gravitational acceleration all at once, without requiring exotic ice chemistry. Loeb was careful to frame this as one possible hypothesis among several, not a confirmed conclusion, but the framing that reached the public was often far less careful, and Harvard scientist says interstellar object might be alien spacecraft became one of the biggest science headlines of the decade. It's worth being precise here. No credible peer-reviewed consensus ever concluded Oumuamua was artificial. The vast majority of astronomers who studied the object, including many who directly disagreed with Loeb, considered natural explanations far more probable and far better supported by the actual data. But the hypothesis was taken seriously enough, and Oumuamua was strange enough that one of the most respected SETI programs on the planet decided it was worth actually checking. That program was Breakthrough Listen, backed by billionaire Yuri Milner and headquartered at UC Berkeley. In December 2017, while Oumuamua was still trackable, the team pointed the Robert C. Byrd Green Bank telescope in West Virginia, one of the most sensitive radio telescopes ever built, directly at the object. Over the course of several hours, spanning a huge swath of radio frequencies from 1 to 12 gigahertz, sensitive enough to detect a signal no stronger than an ordinary cell phone. If it had been broadcasting from Oumuamua, the team listened, and they heard nothing. No structured signal, no transmission, no artificial noise of any kind. Silence across the entire observed band. That result doesn't fully rule out every conceivable form of artificiality. A dormant probe or a passive light sail wouldn't necessarily need to transmit anything. But it did rule out the idea that Oumuamua was an actively communicating spacecraft, and it removed one of the more sensational possibilities from serious consideration. It's also worth noting that the artificial hypothesis, however much attention it drew in the press, was always a minority position, even within the small community of scientists who took it seriously enough to publish on it. The far larger body of published peer-reviewed research on Oumuamua has focused almost entirely on natural mechanisms, refining models of hydrogen ice sublimation, dark comet behavior, and unusual formation histories, rather than treating the artificial explanation as a live, competing possibility. That distinction matters, because in the years since 2017, public fascination with the alien spacecraft angle has sometimes outpaced the actual weight of scientific opinion behind it, and separating what captured headlines from what actually convinced specialists is part of understanding the story honestly. So where does that leave us? Oumuamua's true nature is still, honestly, not settled with total certainty. What is settled is this: the overwhelming majority of the scientific community regards it as a natural object, almost certainly some kind of icy rocky body ejected from another star system, likely during the chaotic early formation of that system's planets, when gravitational interactions with large planets can fling smaller bodies out into interstellar space entirely. Our own solar system does this too. It's ejected countless small bodies over billions of years, and models suggest other star systems do the same at a rate high enough that interstellar wanderers like Oumuamua should, statistically, be relatively common, just historically impossible for us to detect until our telescopes and survey techniques got good enough to catch one passing through. Oumuamua being the first one we ever found wasn't a coincidence of nature bending toward the extraordinary. It was a coincidence of our own technology finally catching up to what was already out there. Now, about that idea that Oumuamua turned back. This is where a lot of viral claims and recycled clickbait headlines have gotten the story badly wrong, and it's worth setting the record completely straight, using nothing but the tracked, published, telescope-confirmed trajectory data. Oumuamua entered our solar system on a hyperbolic trajectory, meaning it was never gravitationally bound to the sun in the first place. It swung past our star at its closest approach, inside the orbit of Mercury on September 9th, 2017, moving at roughly 87 kilometers per second, and it has been continuously moving away from the sun and from Earth ever since, with its speed relative to the sun increasing the farther out it travels along that hyperbolic path, exactly as basic orbital mechanics predicts. By the time it was discovered in mid-October 2017, it had already passed its closest point and was already outbound, only visible because it happened to catch enough sunlight on its way out. It passed the distance of Jupiter's orbit in early May 2018. It crossed Saturn's orbital distance in January 2019. It reached the distance where Uranus orbits in August 2020, and Neptune's orbital distance in June of 2024. Tracking models published by the European Space Agency and Hubble Space Telescope teams show it reaching the outer edge of the Kuiper Belt around late 2025, and it is projected to cross the heliopause, the true technical boundary of our solar system, where the sun's solar wind gives way to the interstellar space, around the year 2038. After that, it continues outward forever toward the constellation Pegasus, never to return. There's been no confirmed telescope observation published by any credible observatory or peer-reviewed journal showing Oumuamua reversing course, slowing its outbound trajectory, or turning back toward the inner solar system. It cannot. Its hyperbolic trajectory and its current velocity make a return gravitationally, physically impossible under any known force besides some kind of active propulsion, and there has never been a shred of evidence for that. Oumuamua left, and it kept leaving, and it will keep leaving for the rest of its existence. So if Oumuamua isn't circling back, why does this story deserve your attention right now, in a way that feels more urgent than ever? Because the second half of that title, the "It's Not Alone" part, is not clickbait. It is, in fact, dramatically understated compared to what has actually happened in the years since Oumuamua vanished from view. For 2 full years after Oumuamua's discovery, it remained a singular event. One object, one glimpse, one set of unanswerable questions, no way to compare it against anything else, because nothing else like it had ever been found. That changed in August 2019, when an amateur astronomer named Gennady Borisov, observing from Crimea with a telescope he built himself, spotted a fast-moving comet-like object that follow-up observations quickly confirmed was, once again, on a hyperbolic trajectory, meaning it, too, had come from beyond our solar system. What made 2I Borisov's discovery even more remarkable is that it wasn't found by a government-funded survey or professional observatory team at all. It was found by an individual, using equipment he built himself, which underscored just how much the search for interstellar objects had already begun, shifting from wait and hope one wanders into our field of view, to something closer to an active, ongoing hunt, involving both professional networks and dedicated amateur astronomers scanning the sky night after night. The second confirmed interstellar visitor was named 2I Borisov, and unlike Oumuamua, it behaved exactly the way astronomers expected an interstellar comet to behave. It had a visible coma, a genuine tail, and clear signs of active outgassing as it approached the sun, confirming decisively that it was a comet in the traditional sense, essentially a normal icy comet nucleus that simply happened to originate around a different star. 2I Borisov gave scientists their first real point of comparison, and in some ways it made Oumuamua look even stranger by contrast, because it demonstrated clearly what a typical interstellar comet actually looks like when you catch one in the act. And Oumuamua looked nothing like it. For nearly 6 years after that, the count stayed at 2. Then, on July 1st, 2025, a NASA-funded survey telescope in Rio Hurtado, Chile, called Atlas, caught something new. Initially cataloged under the placeholder designation A11PL3Z, follow-up analysis confirmed within a day that this object, too, was interstellar, arriving from the direction of the constellation Sagittarius. It received the official designation 3I Atlas, making it the third confirmed interstellar object ever detected in the history of astronomy, and easily the most thoroughly studied one yet, because unlike Oumuamua, which was already leaving by the time it was spotted, 3I Atlas was caught on its way in, giving scientists an unprecedented amount of lead time, months rather than weeks, to plan, coordinate, and point every major instrument on and off the planet at it. And what they found, and are still finding, has been remarkable. 3I Atlas reached perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of about 203 million kilometers, tucking in between the orbits of Earth and Mars, and importantly, posing zero threat to our planet. At its closest, it never came nearer to Earth than roughly 270 million kilometers. Unlike Oumuamua's eerie silence, 3I Atlas behaved from the start like an unmistakably active comet, and it only grew more active as it approached the Sun. James Webb. Space telescope observations, made while the object was still several astronomical units out, detected an unusually high ratio of carbon dioxide to water vapor in its coma, a chemical signature notably different from the mix typically seen in comets that formed in our own solar system, hinting that 3I Atlas may have formed under very different conditions around a different, older star. Then, in December 2025, JWST observations went further, delivering a robust detection of methane in the comet's coma, a hypervolatile ice that only sublimates at extremely low temperatures, meaning its presence tells researchers something specific about how cold and how far from any star the material that built Three-eyed Atlas must have originally formed. As it passed perihelion and began its outbound journey, post-perihelion observations from Hubble allowed astronomers to finally isolate the faint glow of the object's actual solid nucleus from the much brighter surrounding coma, refining size estimates to a nucleus roughly 6 kilometers across, making Three-eyed Atlas significantly larger and more massive than 2I Borisov, the previous interstellar comet. Spectroscopic surveys using instruments like the Keck Cosmic Web Imager, the Spherex Space Telescope, and ground-based observatories like the IRAM 30-meter telescope in Spain and Japan's Subaru telescope have continued tracking the object's chemistry as it heats and cools on its way back out, detecting outgassing of cyanide compounds, iron, nickel, carbon chain molecules, and a coma of gas and dust that at points stretched roughly 700,000 kilometers across, nearly twice the distance between the Earth and the Moon. Observations in January 2026 even revealed that the ratio of carbon dioxide to water in the coma had shifted compared to earlier readings, suggesting the composition scientists are measuring near the surface may differ meaningfully from what lies deeper in the nucleus's interior, evidence that this object's structure is layered and complex rather than uniform. By March 2026, Three-eyed Atlas passed near Jupiter's orbit on its way back out into interstellar space, and it is now firmly on an outbound escape trajectory that will carry it away from our solar system forever, following the same one-way physics that carried Oumuamua away nearly a decade earlier. It's expected to remain faintly visible to telescopes through the rest of 2026 before fading beyond our reach, joining Oumuamua and 2I Borisov as the third confirmed member of an entirely new category of astronomical object, one that simply had no formal place in scientific literature before 2017 because no confirmed example of it had ever been caught and studied. And researchers, including teams from the SETI Institute, have been explicit that comprehensive searches for artificial radio signals from Three-eyed Atlas, like the ones conducted on Oumuamua back in 2017, have likewise turned up nothing but a natural comet's signature, further reinforcing that this newest visitor is exactly what it appears to be. So here is what not alone actually means, grounded entirely in confirmed, published, telescope-verified science, with nothing invented and nothing exaggerated. In 2017, humanity detected its very first confirmed visitor from beyond our solar system, a strange, tumbling, elongated object that defied easy classification and accelerated in a way that still isn't fully explained with total certainty. 2 years later, we detected our second, a far more conventional interstellar comet that gave scientists their first real comparison point. And in 2025, nearly 8 years after Oumuamua first appeared, we detected our third, an object so well observed, tracked from so far out, and analyzed with such advanced instruments that scientists have been able to watch its chemistry evolve in close to real time as it swings around our sun and heads back out into the dark. 3 confirmed interstellar objects discovered across less than a decade after 0 were ever confirmed in all of recorded human history before 2017. That acceleration in discovery rate isn't a coincidence, and it isn't because interstellar objects have suddenly started passing through our solar system more often. It's because our survey telescopes, our detection algorithms, and our observational techniques have become dramatically more capable in a very short window of time. And upcoming instruments like the Vera C. Rubin Observatory in Chile, which is specifically designed to conduct deep, wide, continuous surveys of the entire night sky, are expected by many astronomers to detect interstellar objects passing through our solar system far more frequently going forward, potentially turning what was once a once-in-a-lifetime discovery into a semi-regular occurrence. That's the real headline hiding underneath all the noise. Oumuamua did not turn back. It cannot turn back. It is drifting silently toward the edge of our solar system and beyond, on a trajectory that will carry it back out into the vast emptiness between the stars, exactly the way it came in. But the story of Oumuamua was never really about whether one strange rock might return. It was about what its discovery revealed, that our solar system is not a sealed, isolated system quietly orbiting our sun in permanent solitude. It is a place objects pass through, wanderers ejected from other star systems, carrying frozen fragments of chemistry that formed around other suns, under other skies, sometimes billions of years before our own sun even ignited. Every one of these objects is, in a very real sense, a physical sample of another solar system delivered directly into our own backyard, accessible to our telescopes, our spectrometers, and potentially one day to our spacecraft. That last point isn't speculation either. The European Space Agency's Comet Interceptor mission, currently in development, is specifically designed to sit parked in space, waiting, ready to be launched on short notice the moment a suitable target, potentially a future interstellar object, or a pristine, never-before-visited long-period comet, is detected heading through our solar system. Scientists involved in tracking 3i Atlas have openly described the intensive observational campaigns around Oumuamua, 2i Borisov, and now 3i Atlas as rehearsals, each one teaching researchers how to detect, characterize, and respond faster the next time, so that when the fourth interstellar visitor arrives, and given the accelerating pace of discovery, most astronomers now consider it a matter of when, not if, humanity might finally be ready to do more than just watch it disappear back into the dark. We might, for the first time in history, be ready to send something out to meet it. Think about what that would actually mean. Every piece of information we have gathered about Oumuamua, 2i Borisov, and 3i Atlas has come from a distance, through light alone, filtered through spectrometers and photometers and radio receivers pointed at objects millions or billions of kilometers away, always racing against the clock before they faded from view for good. A spacecraft positioned to actually rendezvous with a future interstellar visitor, even briefly, even just to fly past it and capture close-up images and direct measurements, would represent an entirely different category of science. It would be the first time humanity ever got a genuinely close look at material that formed around a star other than our own sun, material that may have been drifting through the emptiness between stars for hundreds of millions or even billions of years before it happened to cross our path. There is no substitute for that kind of proximity, and there is no way to manufacture it artificially here on Earth. It only becomes possible when the universe happens to send something close enough, and when we happen to be watching closely enough and quickly enough to respond. That is precisely why the jump from one interstellar object in 2017 to 2 by 2019 to 3 by 2025 carries so much weight, and why serious researchers describe it less as a string of coincidences and more as the opening chapter of an entirely new field of observational astronomy. Each detection sharpens our search techniques. Each detection refines the models predicting how common these objects actually are passing through our solar system at any given time. Each detection gives engineers and mission planners more concrete data to design future rapid response spacecraft around. None of that depended on Oumuamua turning back, reversing course, or doing anything even remotely close to what a certain flavor of viral headline likes to imply. The real story was always forward-looking, not backward-looking. It was never about one object returning. It was about how many more objects like it are almost certainly already out there, still undiscovered, still crossing paths with our solar system on their own long, silent journeys between the stars, waiting only for the right telescope on the right night to finally notice them arriving. Oumuamua's true origin story, the exact star system it came from, how long it had been drifting before it happened to cross paths with our sun, and precisely what mechanism caused its faint, ghostly acceleration, may never be fully solved, because it's already gone, already too far and too faint for any instrument we currently possess to study further. But it did what messengers do. It arrived, it delivered a piece of information nobody was expecting, and then it moved on, exactly as its Hawaiian name predicted it would. And in doing so, it opened a door that had never once been opened before in all of recorded human history. And that door has not closed since. 2 more visitors have already walked through it, and neither one turned back either. Whatever detection systems astronomers are running around the clock right now, scanning the sky for the next flicker of unexplained motion, the next object moving just a little too fast, on a path that's just a little too straight to belong to our sun, that search is active, ongoing, and based on everything we now know about how often these things actually happen, it is very likely only a matter of time before it succeeds again.